Hello. So in this live session, you can ask questions. Any questions that you have, please post within next 5 to 10 minutes. So we will be able to discuss or answer those questions. Now, by the time that you discuss those questions, I will discuss briefly what we have covered. So please post your questions and we will discuss what has been covered until now. We have covered until 8 module now. So the first module was about the introduction. So where we covered the basics, that what is a fluid, what are the fluid properties and its application to chemical and biomedical engineering. We discussed about the cardiovascular system, the pulmonary system and other systems in our human body, other organ systems where fluid mechanics plays an important role. And as a result, when we design biomedical devices, we need to take into account the fluid mechanical aspects in the design of these devices. Then we looked at some basic mathematics, for example, vector algebra, etc. And in the module 2, we discussed some introductory concepts, for example, velocity field, shear stress, system and control volume, Eulerian and Lagrangian framework, basically all the terminology that is required to understand fluid mechanics. We also looked at the flow visualization. So when we say flow visualization, we looked at streamlines, path lines, streak lines, etc. In the third module, we discussed the simplest yet powerful technique to analyze a fluid flow problem. It is the power of the technique is that you can do the calculations quickly, and what we call it dimensional analysis. So in the dimensional analysis, we can list down all the parameters on which a particular flow phenomena depend upon, and then we can group those non-dimensional parameters. And the beauty of this is that when we can, using the technique, we can reduce the number of variables whose effect we need to analyze. So we can reduce the number of experiments significantly that we need to do to understand the effect of various variables. Then we briefly also discussed similitude or scaling up of a reactor or any particular device. Then in the module 4, we looked at fluid statics. So where we considered that if the fluid is stationary, what is the hydrostatic pressure? We all would have studied pH equal to rho GH. We discussed the Archimedes principle, how it can be derived from the hydrostatic pressure concept and so on. And then we looked at what are the forces on a surface that is submerged in a fluid, and what are the forces if there is a plane surface, if there is a curved surface, and from those forces we also calculated or we derived the Archimedes principle. Then these 4 modules we discussed in the first live session also. In the last 4 weeks, what we have discussed that makes the core of, say, fluid mechanics, we discussed the two tools or techniques that can be used to analyze fluid mechanical problems, what we call integral analysis and differential analysis. So in the integral analysis or macroscopic balances, we could take a control volume and analyze the flow coming in, flow going out, and the integral forces acting on the bodies or on a control volume. So that is helpful to calculate or finding out the forces on different bodies, but it does not provide us the force distribution. In the next module, we started looking at differential analysis. And differential analysis, for doing that, we need to know that what is the deformation in the fluid, or what is the velocity of the fluid, what is the rotation. So we took a differential fluid element and we did its kinematic analysis. So its module 6 was about fluid kinematics. We looked at the translation, rotation, angular deformation and the linear deformation of a fluid element. So from this we could analyze that for a given velocity field. So velocity field is in general the velocity field when we take it is in the Eulerian framework, and from the velocity field how we can calculate the velocity of a fluid particle, for example, that we discussed and derived the relationships for that, and the useful concept of material derivative, which is not only useful to say calculate acceleration but also to see the variation of any property. For example, in some of the problems or assignments we discussed that how the we solved that how the temperature changes or how the concentration changes using substantial derivative. Then in the next two modules, module 7 and 8, we looked at the differential analysis. So we derived the from Newton's second law of motion, we derived the Navier-Stokes equation or the first Cauchy momentum equation, where basically the momentum conservation principle, and after assuming that the fluid is incompressible and Newtonian, we substituted the relationship between stress and rate of strain, and from that we derived the Navier-Stokes equation. Now what we did is, because these equations are non-linear and it is very difficult to solve them in general for all the problems, it's only in special cases when we can get rid of the non-linear term we can solve these equations. So we solve some of the problems. For example, the flow between two parallel plates, the motion can be for two reasons. One is that if you have the liquid between two parallel plates and the upper plate is moving, there is no pressure gradient that drives the flow. In such a case, you will have a linear pressure, linear velocity profile coming into picture. If you have the flow between two parallel plates and it is driven by both the plates are fixed and the flow is driven by the pressure gradient, then you will have parabolic velocity profile. What we solved is the combination of the two, and because the equations for such we assume that the flow is fully developed, so we could neglect the nonlinear term there, u du by dx or u dot del or v dot del v term. So when that term could be neglected, assuming the fully developed flow, we could combine both the solutions, and we saw that it is combination of linear and parabolic velocity profile for when both the upper plate is moving and there is a pressure gradient to drive the flow. Then we also looked at say flow in a channel, which is the most commonly used solution in number of applications in chemical engineering, in biomedical engineering, in mechanical engineering, in almost every discipline. The flow, laminar, fully developed flow in a pipe, and what we call Hagen-Poiseuille relationships or relationship. And then we looked at some other problems, say for example flow between two cylinders and the flow between and the lubrication approximation, Stokes flow, and so on. So that is what we have covered. So with that, we have now all the tools available, all the three main tools available: the integral analysis, the differential analysis, and dimensional analysis to analyze fluid flow problem. And in the next four subsequent lectures, we will be looking at some simplification. For example, inviscid flow, when we can neglect the viscosity, or we can look, or we will be looking at say boundary layer, so a layer near the wall where the viscous effects are important. So we will be able to decouple the fluid flow problem, the inviscid flow in the outer layer, and the viscous effects important in the boundary layer. Then we will look at the external flows and the flow in pipes. So that is what we have done until now and what we are going to do in next 4 weeks. So if you have any questions, please feel free to ask. It will be good if you can post them in next, say, 10 minutes or so. Okay, so somebody asked, can electrical students do this course? Because this course is a first course in fluid mechanics, and what it requires is an understanding of vector algebra and calculus, and the physics that you would have studied in class 12. So if you if you are able to do those prerequisites, I think you can do this course, and you can find that that how it is useful to you. You can relate it with the concepts that you are looking for to understand. You can change the slide, bring the slide, first slide. First slide. So you can post any question if you have. Or any suggestion, or you want to solve any examples that we can solve in the next live session, or I can make a short video and post it. So please post any questions if you have in next 5 minutes, or we can close the session after say 5 to 10 minutes. Okay, if there are no questions, then we can close the session in next 5 minutes. If you have any questions, please post it now. Okay, if there are no questions, then we will close it in next 2 minutes. Okay, thanks for joining the session. So we will close the session now. Thank you.